Okay, so we're at the 1 minute mark. I'll emphasize, this is optional. Someone said, oh no, so I wanted to point that out. You can play the home game, you cannot play the home game. You won't miss anything, but for some people it's fun, okay? And I just realized, I said Valgrind, I don't use it in this talk. This repo I've used for some other talks on related subjects, but they're not exactly the same. So I don't actually use Valgrind. And someone commented on the title, Scale accepted the second of 2 linked talks, and so the title is slightly less salient, but I like to think it just makes me inscrutable rather than confusing. And I guess that's time. So the title, as you see, is The Young Man in the Sea Reloaded. And what we're going to do is we're going to kind of dive into the deep end of C and C++, and we're going to start with a very simple example. So if you're playing the home game, this is where you find the code. But the only thing we're interested in is this one little function, will overflow. Everything else is kind of driver code, and I'll show it to you. But there are 2 questions I want you to consider. What is the intended behavior of will overflow, and what will the actual behavior be? Okay? So here's the code. Is that visible? Back there, is that readable? Okay. I, at one point, had bolded them to make the green, sort of the letters have a higher contrast, and then the problem was they seemed a little overdone. All right, so the only thing we're really interested in is the behavior of this function called will overflow, and all it does is test whether its parameter n plus 1 is less than n, which of course can't happen in the integers, but of course it does happen in the modular integers. In other words, I'm looking to see exactly what it says. Will this thing try to wrap? Okay? And everything else is just, I try to use it to make a prediction. In this case, I try it on int max, and then we actually do the thing, do the computation. I think I had to move it out of the main, or the optimizer would do stuff. And then it prints, all it's going to do is print the answer. And if you run the little test harness, which actually runs it under several different sets of compile flags, in every case it does exactly what you thought it would do. Int max plus 1 wraps around to int min. I mean, what else could it do? Okay? And with the optimization shut off, it always predicts that. However, if we turn on a bit of optimization, at 01, it still predicts correctly with GCC. It predicts incorrectly with Clang. Now, if we turn on 02, it fails with both compilers, which means the behavior of that code was both compiler and optimization level dependent, and that's not what we want from a programming language. So the question becomes, why? Now, for comparison, I could take exactly the same code. Notice that the only thing I've changed is the fact that I'm passing in an unsigned. And, of course, I have to test it on uint max and see whether it wraps to 0. But other than that, it's exactly the same code. And what happens, again, it always wraps. But in this case, with either compiler, with any optimization level, the behavior is the same. It correctly predicts it. So the question is, why did it work now? Why did it fail before? All right? So what if I told you the first program actually wasn't C at all? Okay? So at this point, now it's red pill, blue pill time. So just like Neo in the movie, I, like Morpheus, have to give you a choice. You can either take the blue pill, and that means the talk ends, and you can believe whatever you want to believe about C and about your compiler. But if you take the red pill, then the talk goes on, and we explore just how deep this rabbit hole goes. Okay? I won't look if you want to sneak out. Okay, so you're still here. You have apparently chosen to take the red pill. All right? So now the first thing is you might say, well, that first program had to be in C. I just stayed here so I could object. The first program had to be in C because the compiler accepted it. I want you to remember something. The compiler is a machine. The machines lie. Yes? Okay? They don't want you to know you're in their matrix. All right. So what we usually think of is that a programming language has a standard, and the standard defines exactly what the constructs of the language do. Isn't that what a standard is for? That's actually true for some languages, okay, and reasonably close for others. It's probably exactly true for Haskell, because they try especially hard in that community. It's a very similar language called OCaml has, I believe, a hole or two because they care more about performance than the Haskell people. However, C and C++ are actually terrifyingly different than any of those languages and pretty much any language designed after C, okay, that didn't actually just inherit it from C like C++ did. So there are 4 other possibilities in the C and C++ standards besides actually defining what constructs do. They have 4 different ways to not tell you what they do, okay? In order of increasing chaos and mayhem, you have locale-specific, okay, which is at least opt-in and makes some kind of sense. You have implementation defined, which is not opt-in. However, at least it has to be documented. Okay? There's unspecified, which means they don't even have to document what happens, and I don't believe it has to be consistent. However, and you might think, well, that's as worse as it could possibly get, and that would be true in a sane language, or at least it would be true if the world were nice. But actually, it's not true because there's something worse. For unspecified behavior, the program does have a meaning. You may not know what that meaning is, and you may not be able to figure it out except by running it and hoping it stays consistent from run to run, but it has one, okay? There is a 4th category in the standard called undefined behavior, and you'll notice it says, upon use of, this international standard imposes no requirements, okay? Now, if that isn't terrifying, if you're not afraid right now, then you must have misunderstood. So what I'm going to do is I'm going to unpack that at some length so you understand just how much worse that is than at least all of us that have gray hair and learned C a long time ago think. So no means no, and there are ways that people have formulated this. A famous Usenet formulation was, it's legal for the compiler to make demons fly out of your nose. The famous nasal demon formulation. The one I like the best is actually at least repeated by Chris Latner, who's an important compiler writer. Any undefined behavior in C gives license to the implementation to produce code that formats your hard drive, okay? By the way, every time in this talk I say C, I pretty much mean C and C++, because on this issue there is no difference, all right? So, well, now maybe Chris Latner won't actually go to the trouble of generating code to format your hard drive. Let me tell you what will happen, all right? Although you might read Ken Thompson's paper on trusting trust, because if you're a high enough value target, maybe he will. But the compiler will absolutely do whatever is fastest, and if you invoke undefined behavior, then that will sooner or later create a vulnerability in your code. And there are many volunteers on the net who will be happy to run code on your computer to format your hard drive so he doesn't have to, okay? And this is not a theoretical thing. Secord works with CERT at Carnegie Mellon, and he points out, you know, the majority of security vulnerabilities in C and C++ programs require or involve exploiting undefined behavior. Okay, and it's not like there's an edge case or two, like in the case, I think, of OCaml, okay, because it lurks everywhere, okay? And I'm not even going to go through this list. I found more than, you know, if my more than 200 here isn't right, I'm not going to count again, thank you. But some of these you knew, but what you knew you weren't supposed to access beyond the ends of a memory block, but you probably didn't understand the consequences of doing it, and that's what we're unpacking now, all right? So the biggest problem is, how in the world did C and C++ end up with a situation where if you invoke undefined behavior, your program actually doesn't have any meaning? And the answer, almost the whole answer, is in this part of the C Standard Committee Charter: make it fast, all right? And C++ inherits all the same thing. There's some of it is sort of the low-level focus, but performance is really the monster, and it's the consequences of uncompromising performance that we're exploring. So a lot of it, when we program, we usually have some kind of a picture of what we are using. And if we have any picture of a compiler, it's usually this one. So there's a front end which does things like parsing and type checking. And then there's a back end that we hope it does a bit of optimization, sprinkles pixie dust on the code. Okay, what that means is, what we think is that the front end discovers the meaning of the program line by line, just like the way we think about it. And the back end then generates assembly with the same meaning line by line. Okay, so we thoroughly think in terms of lines of C++, or if you're a little more sophisticated, maybe you think in terms of sequence points, but it's all the same. The problem is that this leads us to think that the undefined behavior, sure, it's there for performance. What it's really letting C do is use single machine instructions so that addition does whatever the processor does. It's 2's complement if the processor's 2's complement. Null, you can dereference null with undefined results because that way we don't have to put in null checks. The problem is that's not the compiler that you have. Now, if you're old enough, it might be the compiler you had a long time ago when we weren't very good at writing compilers, all right? But that was because compilers were stupid then. They're not so stupid now, okay? So this is more like the compiler you actually have. So yes, there's still a front end and a back end, but in the middle, all the optimization is in this middle end. And I have drawn it the way I drew it because this little tiny piece of the compiler in, I don't know, 1970 or whenever, has become the tail that wags the dog. This is most of the code in your compiler. And the reason for that is pretty simple, actually. Determining the meaning of the program is a solved problem and will not grow without bound over the lifetime of the language. Okay? The same is true of code generation, but we have a theorem that says there's no such thing as a fully optimizing compiler. There's always an optimization left to make. So if you are doing your doctoral thesis in compiler technology, what do you think you're going to do? Yes, that's right. You're probably going to add more code to this, effectively. So the major task of the compiler, still the front end does discover the meaning of the program, essentially line by line. However, then it goes to the middle end. And that middle end is part of an ever heightening arms race between, PhD students and compiler writers, and it's getting smarter and smarter, and it does amazing things to that program and probably erases all knowledge of even what the original source lines were. And then what it produced is handed to the back end. And yes, it does produce assembly code with the same meaning of what it was given, but it gives assembly code with the same meaning as this amazingly transformed program. And the transformed program does not need to have the same meaning as what you wrote. Okay? Now, it does have to have a certain relationship, but the only one is the one imposed by the standard, and I want to go back and point out that no means no. The standard imposes nothing on a program which invokes undefined behavior, really. Okay? So I want to show you how a compiler exploits this because it tends to seem very theoretical. So let's categorize all functions into 3 types. First of all, there are type 1 functions which don't depend on undefined behavior at all. Those are uninteresting for this talk because the optimizer has to behave and do what you think it should do. So that's not interesting in this talk. Type 3 functions always depend on undefined behavior. So that's also uninteresting because the optimizer, frankly, should just simply remove them. Remove the calls altogether because the fastest way to do nothing in particular is to do nothing at all. So the interesting case is type 2 functions, which may or may not invoke undefined behavior depending on the inputs or some other context such as, acquiring a database handle or something. So the optimizer has a lot of license but not complete license. So what should the optimizer do? What are the requirements? Well, first of all, if the inputs are such that there is no undefined behavior, then it needs to do exactly what the standard precisely defines, okay? And it should be as fast or as small or whatever we're optimizing for as it can be for that case. However, if you pass it inputs that do invoke undefined behavior, first of all, there are no rules. The standard imposes no requirements. And optimization in that case is also meaningless because part of the ethos of C and C++ is trust the programmer, and in particular, trust the programmer to never actually do that. All right? So what that means is that the optimizer should analyze and optimize a function based on the assumption that nothing ever invokes undefined behavior. All right? Because that is the fewest constraints and the most latitude for speeding up the defined case. Okay, so let's take an example type 2 function. This is our friend from a few minutes ago, will overflow. I've just, now that I don't have to squeeze it on there with the driver code, I've formatted it reasonably. Okay, now what should it do with will overflow? Well, first of all, it turns out, that the optimizer, so remember, n plus 1 less than n is our test. Well, the C standard says that adding 1 to n is undefined if n is int max. It does not say that it wraps. Okay? So the optimizer should assume that n is never int max because that would be not trusting the programmer. So therefore, this test always produces false because unless it's int max, this is always, the left-hand side is always the larger. So what it should do is produce the same code that it would produce for this function, which simply returns 0. And in fact, that's what it does because that makefile also preserves the assembly language generated during the compilation. And in fact, you don't even need to read x86. This thing takes a register and XORs it with itself. That's an assembly language idiom for loading 0, which now or at some time in the past was faster and or smaller, but anyway, it's an assembly language. And then it returns, why? Well, because clearly we can deduce that EAX is the return value register on x86. So what it did, in fact, was return 0 in the fastest possible way. You'll be glad to know that was optimized. All right? So what happened, now you know what happened. All right? Will overflow is a type 2 function, and I passed in an argument that invoked undefined behavior. So that means it has no meaning according to the standard. It's not C, and in particular, its behavior cannot be predicted from the source in that case. The unsigned analog was a type 1 function because the standard actually says that uint max plus 1 is 0. It says it wraps in all cases. So now you might think, well, okay, that was weird, but I've written C, and it didn't seem to always do that. So I want to kind of show you how bad it can be. What if we modify this slightly? I'll do the test differently. I'll check whether n plus 1 is equal to int min. Now, within C, that should always be the same. That should always produce the same results, at least for the way I drove it. Okay, but what actually happens if we test it? Well, once again, it always does actually wrap. However, with GCC on O2, it again fails to predict that it will wrap. Every other case succeeds. Somehow, before, GCC did slightly better than Clang. Now, Clang is actually making the code work all the time, and GCC is not. Okay? What I'm trying to show you is that the results don't, when you get into the area of undefined behavior, the results can not only depend on the compiler and the optimization, it can depend on details of the source that look completely equivalent. Okay? In fact, you can get instability from release to release. I just randomly pulled a bug report out of the GCC Bugzilla. A Bacula developer was unhappy because G++ 6.0 started deleting his checks for whether this is null. Well, so how many of you are C++ programmers and actually got a chill down your spine when I said testing whether this is null? Okay, so yes, that's right. The standard says that that does not happen, and so the optimizer correctly recognized that and removed them. I don't know what he was up to, but it was not the right thing. He also was unhappy about one that seems to be very well known, I hope, at this point. It was deleting calls to memset. Why? Because in the C virtual machine, when you release memory back with free or delete, it's gone. And it doesn't matter that it used to contain your bank account information because it's gone. But of course, in the real world, we like to zero it out. But if you zero it with memset, the compiler knows way too much about memset. And it will look and say, oh, he memset it to 0, then he freed it. The memset had no effect, and so it'll remove it because it's faster. Okay? There's a just as a free tip that's not in the talk, there is in newer Cs, there's a memset underbar S, which the compiler is forbidden to touch. And if you don't have that available to you, write your own, stick it in a compilation unit of its own so it can't do any interprocedural optimization, and trick the compiler into not pulling it out. Okay? So some of the responses on the Bugzilla are quite enlightening. The developer was told, you seem to be confusing it worked okay until now with this code is valid. Or someone more concerned said, it got smarter. And that's what happened. The compiler got smarter, and his incorrect code, which had happened to be working, didn't work anymore because the optimizer was smarter now. Okay? In fact, the standard permits time travel. Doctor Who loves C. Okay? And the reason is that when it says no imposes no requirement, it really means no. So it means that it is permitted, according to the standard, to find undefined behavior, travel back in time and change its mind about doing something sane that it did earlier and do something insane instead. And this actually happens. Okay? And just because that's so bizarre, there's a good reason for that. The reason is, well, it's speed at any cost. But if you want me to elaborate that, the point is that the meaning of the entire program is retroactively undefined, and the reason is it allows more aggressive instruction reordering, which can be a big win on a modern compiler, but it means that if you're hunting a bug which involves undefined behavior, printf, even good old printf may fail you because the error may not be happening at the point, the error may not occur in time where it looks like it should based on its position in the source. All right? So what I want to do at this point, having said that, I want to give you a tiny bit of a different language to say the same thing, because I think it's useful, and it's my talk. When we say a language is safe, I claim we mean something very specific. It doesn't mean, or we should, it doesn't necessarily mean it's easy to use. What it means is every language creates a virtual machine. It creates an abstraction layer for you because the reality underlying it is too hard. And if you think that it's not too hard because you like assembly, I was a physicist once, and I'll keep going down the stack of abstractions until you don't want to do it anymore, which probably will be sometime before quantum field theory. All right, so the point is, what we really mean is that the virtual machine cannot be broken from within. Now, of course, we can break it from without. If you're running a computation and I pull the power cord out of the wall, what happens will not be according to the standard. But that's okay, because of course I can break it from the outside. C and C++ are not safe in a strong and objective sense. Undefined behavior is exactly where the abstraction can be broken from within. And that means that C and C++ as abstractions are leaky abstractions. They're glitches in the matrix, all right? Because you thought you were in the matrix, and then you hit a glitch where the simulation didn't work. And the fundamental reason why the source code is no guide to what happens is because source code only has meaning from within inside the matrix, meaning within inside the abstraction. Okay? And that is the terrifying reality of C++. So I wasn't joking when I said the first program was not written in C. According to the standard, it had no meaning. And so the compiler wasn't really obliged to do anything much, so what we got was probably more than we deserved. It actually like printed and terminated and stuff. Okay? So now you swallowed the red pill. You know why, and you know why the compiler accepted it anyway. Because it chewed along with the assumption in good faith that I would never pass it anything that would invoke undefined behavior, and I did. So remember, the compiler is a machine. The machines lie, and they may hurt you if you try to use glitches in their matrix. So this leaves us with the question, well, now what? So we have three options. Well, in the movie, if you recall, Morpheus wasn't really right that there's no turning back because, of course, Cypher got a second chance, didn't he? Or at least it looked like it. So you can go back and take Cypher's choice. You can go back to writing naive C and do what seems to work. You can take the red pill and figure out how to cope with reality, as awful as it is. There is a third option, because of course the movie wanted to make you make the same choice Neo did, so naturally they would not bring to your attention you had a third choice. You could stand up and walk out of the theater. And we can do that by abandoning C and C++ as individuals, but it's not practical as an industry. There's, first of all, too much legacy code. More importantly, a lot of the ways that we avoid using difficult languages like C and C++ most of the time is by using them to write the critical parts that actually don't work in our more comfortable languages like database servers or native extensions to our languages so that we can get those little bottlenecks done. So the point is, this is not really practical for us as an industry. Also, it's against my principles to give up and let the machine win, but that's me. And I guess I should point out, while we have very few suitable replacements, whenever we do have one, the industry steadfastly refuses to adopt it, so it doesn't matter. Because apparently inertia is the key to technology. The blue pill actually doesn't work either because unless you have very modest goals for security, reliability, maintainability, and so on, it doesn't work because this is where we are. The reputation for C and C++ as being difficult to program in and bug-ridden is really founded on this. It's not manual memory management, which I actually do a talk and teach how to do systematically. There is no system, okay? So we're left with what I'm going to call the red pill approach, which of course is that because I say so. And that is, don't try to know all 200 edge cases in C. Learn to avoid them instead effectively. You build your own abstraction layer by learning what kinds of programming habits will stay away from those dark corners and sharp edges. And what you do is you do them even when you don't need to, until they become habits, because you know what you will do at 3 a.m. on a deadline is whatever your habit is to do, not whatever a smart person would do at that time, because you're not a smart person at 3 a.m. At least I'm not. Okay? And then what you do is there are values, common values between your habits. You internalize those, and then you practice in depth by using tools, which we don't do enough. And finally, occasionally people object, well, but it really, really does work. The answer here is you can't let the perfect be the enemy of the good. It's very hard to do this. Most non-trivial code bases do have undefined behavior in them, at least even high-quality ones. But you can systematically reduce it. And that really is what you do if you choose not to abandon C and C++ or you abandon reliability entirely. Okay, so the problem is that a long list of sharp edges and dark corners I don't think makes for a very good talk. I don't think that's the way to learn it. What I'm going to do is, first of all, I tried to spend quite a bit of time to make it clear to you why this really is an issue so that you can read things with intelligence and be able to interpret for yourself what the consequences are. And I'm going to do a couple of sort of extended examples as to how I approach this. And then I'm going to give you some references at the end where you can look for more grubby little details on which jagged, rusty edges can cut you. All right? So let's start with the example I've already given you, okay? And that's will overflow. And what I really want to know is not how I can fix this piece of code. I want to know how I can fix all the code I'm going to write in the future. And I'm going to suggest, to start with, I'm going to suggest that you make it a habit to actually prefer using unsigned variables when you don't specifically need the sign. And the reason is pretty obvious. Why? Because their arithmetic is far better defined. The point is a lot of people will loop on int. Why? Okay, there's absolutely no meaning. What that means is a sign, as a non-negative quantity. The number of elements in the array, or the size of the array, is a non-negative quantity. So, in fact, you're actually violating kind of the implicit contract with somebody else reading your code that you chose your types to mean something like what they really mean. Okay? Sometimes it's actually hard to do. I will say this. I have found that removing unsigned, oftentimes, even if it required some fiddling, has tended to improve the quality of the code, and I uncovered places where I or someone was a bit fuzzy about what they were assuming. okay? But I'm not saying you do it for that reason. I'm saying you do it because you're trying to make it so that I don't, when I read your code, I don't say, did they do anything undefined with overflow? Oh, no, it's unsigned. I don't have to look for that. I can go on and look for other things. All right? So as a trivial example, of course, this is what quite a few people do and should not be done. It probably has gotten worse because nowadays a lot of people learn to program in a nice, safe, interpreted language that uses big nums for integers. And C uses big nums nowhere unless you go to a lot of work to use a library. The nice thing about this is that size T is not only unsigned, but the standard guarantees it's big enough for any array that you can obtain in C. So actually we should have been doing that anyway, because the meaning we wanted to express was a size, and that's what we should have done. Now, sometimes it's not that simple, and the reason it's not that simple is that oftentimes somebody else or us has used a whole bunch of signed variables everywhere else in the code, and actually, even though it's not undefined, it can sometimes be tricky to deal with the overflow, even for unsigned. Also, if you're dealing with both signed and unsigned quantities, it's actually a pain in the neck to do the conversions and comparisons correctly according to the standard, although they often are just implementation defined, so at least they don't make your whole program meaningless, sometimes, usually. But my point is that a lot of the reason is because someone started doing bad things and then they made more things and more things signed, so the compiler didn't tell them they were doing bad things. And that's what you have to reverse. And so it tends to be infectiousness, so at least get the good infection and try strenuously to use unsigned and let that infect your code instead of signed, unless you actually need negative quantities, okay? And my point is, and I'll keep coming back to this, hard may be hard, but anything is better than leaving hard within the abstraction is always better than breaking the abstraction and being at the whim of the optimizer, okay? And if you don't agree with that, please don't write C for me. Now, there are actually some nice things that, didn't exist a long time ago. So those with the gray hair, probably have habits to not do these. But the C committee is not entirely made up of insane individuals who hate us. It just seems that way. But there are some sizes which actually express things that we often do with things that don't express those sizes, like ints, which are large enough to hold any other integer so that you can control the conversions and do things that make sense, or pass them to printf and know that they will work. That's another way to do it. If you need to do something non-portable like hash on addresses, you'll have to be non-portable, but remember, non-portable is better than undefined, okay? It's also, if you don't have one that already means what you want it to mean, you're still probably better off with something explicitly sized than int, so that at least it's consistent from machine to machine. And then please type def it and document what that, int 32 here doesn't mean the same thing as int 32 over here. Thank you very much. Now, one of the reasons you have a lot of signedness is because libc sucks. Now, I'm sorry, occasionally a Unix graybeard gets unhappy with me. I'm sorry, but it's true. libc sucks real badly. And here's an example of it. Read returns a signed size t, an S size t, and the only reason is so it can return -1 so that you know to check error no. Okay? Now, the problem with that is, of course, if you know what size, if you want to compare it with the size of your buffer, and then that leads you to want to keep the size of your buffer with a signed quantity so that the comparison all makes sense, and pretty soon everything is signed, all right? So what you do with this is you wrap it, all right? Aggressively wrap things that don't meet your standards, and libc is a primary candidate for wrapping the whole stupid thing sometimes, or lots of it, because notice what I've done here. Whatever you're using for error values, okay, you return, what I did is I passed in the place to store how many bytes were read, because you'll notice now this can be an unsigned thing that actually means what it really is, a size, and I have separated the results in the error codes, because what people are doing when they return a meaningful non-negative number or -1, or they return a pointer or null, is they're actually faking an algebraic data type, if you know what that is. If you don't, it doesn't matter, but don't fake them, okay? If you don't have them, don't stuff things together and use variables to mean multiple things. This ends up meaning function parameters. You shouldn't have in-out parameters, which is a rule that a lot of people know, but is quite beloved in the C community because it might save 4 bytes on the stack. Remember, okay, so if you really mean at any cost, then I can't help you, okay? So the point is wrap aggressively, all right? And in fact, a piece of advice I got, I love this title, I abuse it all the time, make the compiler your Batman. So I got this from a book written by, I think, an Australian who, it turns out that he got a lot of responses to the first edition, because it turns out that in British Empire speak, this is like British Army lingo for your assistant. But I liked the image, the unintended image of the compiler putting on a cape and cowl and skulking in the dark, striking fear into the hearts of cowardly bugs, that I abuse this at every chance. Okay? One of the other responses to that same bug I showed you, same bug report, was someone noted there's an option to disable both of the things that bother you. Okay, actually it turns out that most of us spend a lot of time understanding our languages and apparently no time understanding our compiler. And we should probably not do that because the compiler actually has, when I say the compiler, I'm largely thinking of GCC and Clang. If you use a proprietary compiler, it's still probably true, but you'll have to look, okay? But you can guarantee it with GCC and Clang, and this is a Linux conference, so I don't feel too bad about that. There are a lot of useful flags, okay? And you can do a lot of different things. Some of them will catch compile time errors, okay? In fact, a lot of them, some of them will cost you in some way, but a lot of these are actually free. They don't even disallow things you might have wanted to do. The only reason they're off is fabulous amounts of legacy code, because in 1977, somebody didn't realize that you shouldn't do whatever they were about to do, okay? And so a lot of things are turned off. That's why, how many of you use WALL when you write in C? Okay, I'm a little disturbed it's not everybody, but it's a lot of people. How many of you use W extra? Okay, quite a few people. So those of you that have gotten to WALL have gotten to W extra. How many of you use any other flags besides those that control the interpretation of the source? Okay, I see a few people. Thank you. You guys are in the advanced class. What I really mean is that you can do that, but you can also put in runtime checks, which you may or may not decide you can afford, but let me give you a clue. You can afford them when you're running your test suite, can't you? Okay? Or you can actually change the language into some dialect of C that you find more congenial than the one that ISO envisions, all right? So, you know, maybe the machines aren't entirely evil. Maybe if we ask politely, they might be a little nicer. So, for example, here are some flags that are useful for this particular example I'm talking about. W strict overflow will warn you when the compiler has used the knowledge that something might overflow to optimize. You don't know if it's okay, but at least it warns you that you might want to look and make sure that that's what you meant, because, of course, you can use that even if you're optimizing so much that you're actually using this. It might not be a bad idea to check every once in a while. You can actually have no strict overflow, which essentially tells the optimizer, yeah, don't get so crazy about optimizing that. I don't really know why you'd go halfway, because you can go the whole way. There's an option called FWRAP-V, wrap with a W, which actually fully defines signed arithmetic to be what you probably thought it already was, which is 2's complement. All right? And you can write in that. I'm quite sure that Postgres is written in that dialect. Okay? And you know what? It doesn't seem to have slowed down Postgres. You know what? I didn't put in the talk, and I should have. Let me just give you a piece of philosophy. One of the nice things about writing in a fast language is you don't have to squeeze every cycle out of it, because you probably don't need ultimate performance where you might if you did it in a slow language like Python. So you don't have to go the whole way, all right? And in fact, you probably shouldn't unless the profiling says you can't do it. So what about runtime checks? There's a similarly named FTRAP-V, which actually will check at runtime and trap on signed overflow. Okay, there's an fsanitize option. I believe the sanitize family may have come from Clang, but GCC has them now. F sanitized signed integer overflow. Now that sounds promisingly named, doesn't it? Okay, so what it does is it prints a diagnostic, which probably you didn't want to do in production, but might be awfully handy in testing. Okay? And you can even tell it, hey, try to recover from this and continue. Maybe I could find more errors. I probably wouldn't use that to go to production, but you know what? I'm not your release manager. So there are also some, I don't have time to talk about conversion, but there are some things that will help you if you take my advice and prefer unsigned. When you do have to do some conversion things, there is a WSign compare to warn you about comparisons that might produce incorrect results. You can at least check them. And if you know they're okay, maybe you can find a way to make the compiler shut up by, say, putting in explicit checks rather than just letting people, you know, figure it out for themselves somewhere down the line. There's also WSign conversion, which does the same thing, okay? It's enormously helpful to have the compiler be your Batman here, whether you think that means assistant or the Dark Knight. I want to point out, when you change the dialect, even if it does not meet your goals or your policy to write to a dialect of C, it's still very handy because if you are actually writing to ISO C, for most of these flags, your test suite should produce the same results. Now, shouldn't it? So even if you're not writing to the dialect of C where signed quantities wrap, for sure guaranteed, it shouldn't change the results of your program, okay? You can do the same thing with more than one compiler because they won't do the same and they all need to be the same if it meets the standard. So what are some habits that can let us do this all the time? Well, one habit is maybe we should actually get to know our compiler and take it out for coffee instead of, you know, putting in WALL, WExtra, and then hoping we never have to read the man page again. And choose those flags as carefully as you write code because, you know, the compiler knows more about your code in certain ways than you do. More importantly, it doesn't matter whether it's right or not because it wins. Okay? Remember, non-portable is still defined and it's still better. There's no upside to being at the mercy of the optimizer. Okay? Now, here's another example. This is an extremely simplified actual Linux kernel bug, so that's why the names are kind of odd. The only thing that matters here is I'm passed in a pointer to a struct, and I'm going to have to do something, okay? And what I'm going to do with this pointer is I'm going to obtain another struct pointer. I'm probably pulling it out of this, but it comes from somewhere. And then what I'm going to do is there's a particular field in this that I want to do something with, all right? However, this could be null, and so I'm going to check that it's null, and if it is, then I'm going to return. I'm guessing that that's what this function might have been doing, but it doesn't matter. I'm going to return, and then the rest of this, I'm going to actually use the value that dev points to. You probably already see the problem. What is the problem? The programmer was probably doing the following. Well, okay, what if I receive null here from dev? Well, this value is undefined if dev is null. On the other hand, I'm not going to use that undefined value, so it does not corrupt my program state. The problem with that is that, I mean, that's the same thing you would use for an uninitialized variable, right? You should initialize them, but if you don't, they don't have to corrupt your program state. The problem is the optimizer is the one that wins, and it says, oh, this is a type 2 function. I can optimize this on the assumption that dev is never null, okay? And then I can delete the null check, okay? So how are you going to fix this? Well, again, you have two possibilities. You can eliminate the behavior, which is undefined according to the standard, or you can define it so it is predictable, okay? If we want to eliminate it, the kernel is written in more or less C89, so I have to have all my declarations first. So I'm obviously going to put the declaration before I compute the value, and of course, I hope we're all adults here and we do know that you at least assign, you don't just leave uninitialized variables laying around as a matter of habit, remember? Okay, then I test it, and now what happens is the optimizer comes to this and says, oh, I haven't done anything with this thing. I don't know whether it's null or not. I better keep the test, all right? Okay, the other way is, of course, if you're in C99 or C++, I personally would do this, but Linus does not like mixing declarations and executable code, so if it's the kernel, you'll do the other, and either is fine. The thing that's not fine is not defining it at all, okay? And the bottom line here is a subtle point, but a profound one. I lied to you when I said what the author was thinking, or guessed. Of course, I said this value is undefined, and the compiler doesn't think the value is undefined. It thinks the code is undefined, and there's a big difference. All right? So how do you make a habit of this? Well, this is actually a habit that I came to at some point, and for more reasons than this, but this is certainly a big one. I make a habit of always laying out my code so that all values get sanitized at the earliest possible moment. And sometimes, you know, your brain tries to kill you or try and tell you that, well, wouldn't it be better if I get my stuff and then I kind of collect all the tests at once? Yeah, it occasionally sounds attractive. I don't do that anymore because I want to couple them visually, all right? So, in fact, the first thing I'm going to do in a function is sanitize parameters. Okay, then the next thing I'm going to do is I'm actually going to acquire resources first. And there are other reasons besides this talk that I do this. I will acquire resources and immediately sanitize and reality check them before I go to the next one. And when I have all my resources, I'll do everything else that might have a non-recoverable error. And then at the very end, okay, now I know I can meet my contract, and I'll do that. But I'll lay out every function that way even when it doesn't matter, because I'm talking about habits. So it kind of looks like this. I had to smudge everything, of course, but I just used the same. It didn't sanitize the input, but generally you would, okay? So, right? Hey, if you passed me null, if I'm not allowing null, all right, I'm just going to bomb out right now, whatever your error handling schema is that you have chosen. Otherwise, I will obtain a resource with that, and then I will check and see if I actually got it. If I didn't, again, I'm going to get out as soon as I can. Otherwise, I'll acquire yet another resource. And I'll check that, and then I'll continue, and everything else, of course, will assume that I have resources, but I will lay it out that way in cases where there's not that much going on and it would be clear. Why? Uniformity, because I'm making a habit so that it'll still work at 3 a.m., okay? In fact, more generally, if you really want to think about the principle that underlies that, what I will do is I will first determine if the caller has met his contract. And if not, I will get out right then and there. I won't try to interpret it anyway. And otherwise, I will first do everything that might cause me to fail to meet my contract. And if I fail to meet it, I will undo anything that needs undoing, and I will get out. And only then will I do the rest of my work, which now I know I'm going to meet my contract. And that, to me, in the long run, if every function is done that way, even when it doesn't seem to matter, I find that in the long run it pays off, okay? So there's another underlying value, right? Do common tasks the same way every time. If I loop through an array from 0 to size minus 1, and I test, you know, whether the index is less than size, I want you to do that and not loop on whether the index is less than or equal to the last element. Why? It doesn't formally matter, but in C we have an idiom. We track arrays with size, not last index. Please do that so that we all read code rapidly. And that's really the underlying thing here. I'm trying to make something so that I can do it the same every time, everywhere. Okay? And I want to make it look correct. So I always want release code to sit next to I want sanitization code to sit next to the code that obtains it if possible. And in other words, I want logically coupled code to be visually coupled to the degree that I'm able to do that, okay? The other way to solve this, of course, is once again, define the behavior. This may be the best named flag in all of Unix or all of computing. No delete null pointer checks. It just does what it says right on the tin, folks. Okay, what happened here is that this is what the kernel team actually does. And also, by the way, bind does this. And at least for the kernel, I don't think that the issue was they didn't want to fix that piece of code. It was that they expected that they probably had 1,000 other sites where that had been done. And it had always worked. But remember, you can't depend on that to stay forever. And so, as a workaround, they basically now write in a dialect where it's okay to do that. So, one value, and if I kind of have to sum up everything, it's the phrase, don't normalize deviance. And I got that phrase from an analysis of the Challenger accident. And the point was that stuff is falling, insulation is coming off the tank. It's not supposed to. We don't know why, but it never seems to hurt anything. So we'll take the deviant behavior and we'll just sort of define it to be normal. Don't ever do that. Either eliminate the undefined behavior either by getting rid of the code itself and changing it, or by defining it with a compiler flag. Okay? Because again, and this is the thing I keep repeating, what matters most? What matters most in life, Conan? Well, what matters most in C is not being at the mercy of the optimizer. All right? I'm basically done. I want to point out the only tool I really talked about was the compiler, and the reason is that that's low-hanging fruit. If you don't have a compiler, you're not writing C. If you are writing C, you have a compiler that will help you if only we actually check the docs. And I'm ashamed to tell you how long I used C and never really looked for things like this. But there are many other things you can do. For one thing, there's a whole lot of other flags that you can choose depending on just how much responsibility you're willing to keep your code base clean. Different compilers will find errors in different ways, just by the accident of the implementation. And you really would like it to be clean on every compiler you can lay your hands on, all right? Clang actually has a static analyzer project, and most static analyzers cost money because they're boring to write and hard. Clang has a static analyzer project. You already know, I hope, who here does not know what Valgrind is? Immediately go and Google it, because if you write in C, you want to know what Valgrind is. And there are a lot of things like that. It's not part of the talk. Actually, D and Rust are things that would save us trouble, but we can't do that because we're computer people and we don't change our languages. That's it. I want to leave you with a couple of other quotes. Winston Churchill served in the Boer War and said, nothing in life is as exhilarating as being shot at without effect. And that might be how C feels, but you might as well make lemonade out of your lemons and kind of enjoy the kind of control that you get, because you're going to suffer the sharp edges anyway. And that might even be why C is fun. All right, so that's it. I'm done until I'm kicked out, which is probably immediately. Here are what I think are the most useful places to begin reading. It's hard to actually find these things documented the way I said it. But these two are actually blog posts. Both of them are extremely good. There's also an entire book called Secure Coding in C and C++, which comes out of one of the people at CERT, at Carnegie Mellon. And I highly recommend all three of those to begin your journey. What I hope I've done, though, is made it so you understand why the journey is important, and so that you can intelligently interpret sort of the many grubby specifics. And with that, I'm done. I did, by the way, put cards on the back if you want to talk and we don't get a chance to talk at scale, or you want to pay me to do things that hopefully are sane like this. All right. Any questions? Yes?
So the compiler will claim that function prototypes don't match functions if you can say size.
Yes.
If I put in a separate statement where I cast a variable from integer size to, my code review is saying you don't have any cast.
Okay, all right. So first of all, at some point, you have to live within your policy, even if it doesn't make sense. But what I would do is, in almost every case like this, I only want to do it once. And I don't want cast sprinkled everywhere either. So what I will tend to do, I think with more ferocity than most people, is I will wrap things I don't ever want to see again. And I will do it at most once. If I have an impedance mismatch, what I really don't want is to fix that mismatch at every place I call it. And so what I will do is I will essentially write a wrapper that has the interface I wish I had, and then I will get it right once. Okay? Now, if your reviewers can't do that, then, well, it would be nice if you would get better reviewers, because I'm sorry, that is the right way to do it. But again, you can't eliminate every use of signed either. There are times when you need it, but there are an awful lot of times when you don't. I don't know if that helped you, but I would wrap them, and I wouldn't put casts everywhere, because you have to read up on the cast. That's very problematic too. Yes?
Why would the cast be worse than
I would say it's not worse, but that is a matter, I'm not your code reviewer. There is a reason why Go, which was designed by very old-fashioned graybeard C hackers, pretty much took all the implicit conversions out because they finally got a chance to walk it back after decades. Yes, implicit conversions are horrible. I have not. I have seen some PL1, and I must say I was sort of amazed, but kind of glad I wasn't using it. But if you think about the age, everything older than C starts to get worse rapidly. C actually taught us many things that we weren't ever going to do again. Other questions? You in the checkered shirt, I think you were up first. My opinions about pointer ownership. Well, as it happens, did I pay you to do that? As it happens, I actually have other talks that I've been known to give, and I have an entire talk or section of a talk where I try to systematically teach memory management in C, largely because I've never seen it done, and I learned it the way most people did by, I'm making fewer seg faults this month than last month, I must be getting better. And when I do that, I explain it entirely in terms of ownership. So my opinion is that if you're not thinking in terms of ownership, you're probably doing it wrong. You're certainly doing it wrong if no one can think about it in terms of ownership. In C, okay? I saw you first. Yes, sir. Well, the answer is it could point at that, but it doesn't point at that at compile time, and the compiler doesn't care, right? So it just does whatever the compiler does, and generally in C, it's actually explicit. Trust the programmer. This must make sense somehow. The point is though that the problem again is not invalid data. That's a problem. In most languages, that would be the scariest thing, is to not understand your program state. What's scarier is to not have a program state, because you have no well-defined program, okay? And so the problem there was far deeper than, this might point at something, something I can't touch, or even, well, in main memory, it's not going to trigger an interrupt because you have a number which happens to be interpretable as an address. But it doesn't matter, because the point is that even well-defined mayhem is still better than undefined mayhem. But the compiler, honestly, must have been okay. I trust him that when it was returned from that other function, it won't have returned null, because if it did, that would be crazy. Yes, sir. Okay.
Why was there so many returns? The second part is lambdas. How do you feel about lambdas? And third is the same, almost hitting on the same point, but the known new as far as 14 is concerned.
Okay, so the first part. Let me hit the first one. So the first one was. Yeah, I will repeat it. I wanted to listen. So tell me again. I wanted to hear all of them. The multiple returns. Okay, so the question was, I did a whole bunch of things like multiple returns, which your programming teacher in college, I'm exaggerating for effect, but my programming teacher didn't like them. Okay, right, well, you have invoked my undefined behavior, because now I get to rant for a second. What you have touched upon is a glitch in the matrix where what teachers of programming say does not actually fit the needs of the industry. This is my opinion, and since it's the end of the talk, I can be a little edgy. The fact is that, yes, there was a time when people energetically pushed the idea that every block of code should have a single entrance and exit, and since a function is a block of code, it should have one exit. That's the origin. Now, let me tell you what happened. And Dijkstra, Edgar Dijkstra is the most famous exponent of this. Let me tell you what happened. Actually, let me ask you a question. Do you know anything about chess? Okay, so do you know how you implement chess on a computer? Okay, well, so the answer is you do it very differently than a human being does it, okay? Because a human being is actually not very good at looking very far ahead on dozens and dozens and dozens of lines. But we're really, really good. Well, not me personally, but a master chess player is very good at recognizing lines which don't make any sense by essentially pattern recognition. So we are not very good at following trees, but we're really good at pruning them. Computers are essentially the opposite. Okay, computers are really good at following many. So the point is that for a computer chess player, you will get a lot more of your ability to play from things like look ahead than a human will, and less from your position evaluation. Why do I say that? Let me tell you the dirty little secret about that. The people who benefited the most from the idea that blocks of code should only have a single entrance and an exit were people who wanted to prove theorems about code and people who were writing compilers. And what they're really saying is do a piece of what the compiler does, because if you look up basic blocks on the internet, you'll find that that's pretty much what the compiler does internally. The real question for me is, as engineers, does this help us? And the answer is it does not. Because we are good at pattern recognition, and okay, so the bottom line is that you have two choices. You can have one exit and have code nested more deeply, and sometimes guard the whole thing with these big ifs, or you can bomb out early. And the problem is that the way we actually understand code, I claim, certainly what I do is I read down and I like to know, okay, you know what? I can quit thinking about null because I've just checked for it. So as far as I'm concerned, multiple returns are not only fine, but there are 3 cases where I will accept goto. Now, only 3, unless you can convince me that I missed one. But the fact is that when you do exception handling in C, the idiom actually is probably to use goto. But that's not what this talk is about. The bottom line is that I do that because I actually think it's clearer. And, you know, at this point, I don't usually rant about that because that argument is so 70s. Except you still get people who come right out of school and they don't want to do those things. And so that was, I don't know if that was the answer you were looking for, but it certainly is. I'm perfectly willing to do that. Okay. So the second question, actually I should probably.
Make it even better.
Okay.
Define versus, creating macros versus.
Oh.
Going with templates.
Okay. Oh, macros versus, well, templates are really only C++.
Yeah.
So if you're in C++, of course, you can find a way to not use a C macro for almost everything, and you should. So, I mean, that's almost uninteresting because even if templates are confusing, they still make some kind of sense within the type system. So, yeah, I mean, I would use a template pretty much anywhere if I could avoid a macro. You could probably find a case where that's not true. But in C, it becomes harder because you don't have the templates available. Anybody else? Yes, sir.
You mentioned writing unit tests.
Yeah.
What tools or library do you use to make it easier to write tests, unit tests?
You know, it varies somewhat on the project. I can't remember the name right now. There's a very nice unit tester for C. Let me tell you instead what you should look for in a unit tester, all right? As long as you're doing the test on, a real computer, the way a C unit tester should work is it should fork off before it runs every test, because in an unsafe language, there's simply no other way to keep bugs from possibly screwing up whatever your tester is, okay? And there's one that I just can't remember the name. But the funny thing is that if you're writing for an embedded system and you want to run your test on the embedded system, you probably don't have fork available. But you know what? There is okay, so I'm forgetting all the names. There is another unit tester which is almost the ununit tester. It's like 5 lines, it's like a header file with like 5 lines of C that you include, which actually lets you do it quite easily. So it turns out to be really easy to do, and although I'm kind of unhappy that my brain has quit working, it's actually very easy to find on Google. But what you're looking for is either one which is smart enough and has enough machinery to fork off the test so that you have the process boundary between the code which might be writing crazy stuff to crazy places and the code which is supposed to notice that it did it. Or you probably want to make it really simple so you can run it on anything that can run C. Okay? You know, I really should have those names on the top of my head. I'm sorry. Anybody else? So, looks like maybe we're done. Thank you so much for coming. I have cards at the back if you want for some reason.